Our next talk is Martin Saska. He's going to talk about closely cooperating teams of agile aerial robots in the wild. And after this talk, we're going to have a poster session, so please stay and grab your coffee and come back to see the posters. Thanks.
So, hello everybody. My name is Martin Saska. I'm from Czech Technical University in Prague. Thank you very much for inviting me to be here in this workshop. I believe our research is very relevant to the topic of the workshop because we are one of the few groups, drone groups, without any flying arena. So that's why we have to fly in challenging environments always. We are not allowed to fly in the center of the Prague. We are not allowed to fly in the building. So we really have to fly in challenging outdoor environments, indoor environments. And I will try to kind of summarize the challenges we are facing and the experience we got during our journey towards deploying of teams of aerial robots in the wild. My presentation can be split to two parts. In the first part, I will kind of briefly tell you about a little bit more history about maybe 7 years of research of swarming in the challenging outdoor environment. And then I will summarize the challenges we found, kind of, and show you some current research we are working on in these days. As has been mentioned, I'm kind of a head of multi-robot systems group at Czech Technical University in Prague. We have currently more than maybe, including students, 60, 70 people working on drones only. So we are really focused on flying robots with onboard autonomy. We are proud of several success achievements in competitions, the DARPA SATI challenge, which has been already mentioned here, the MBZRSC competition, and many others where the field deployment of multi-robot systems was the key. Let me start with this slide, which is quite old. I presented this maybe 8 years ago on my grant application. At that time, I wanted to motivate my research by flying in the forest because I like nature, and in my opinion, this environment is quite challenging and it is really wild. We wanted to do some really cooperative swarming system which would work in GNSS denied environment. Clearly in forest you don't have GPS, also in indoor and many others, even urban environment, the precision of GPS is not available or not sufficient. We didn't want to use any kind of communication, mainly because if you are talking about really large groups and you are talking about scalability, the communication is still bottleneck. So we wanted to avoid the communication at all. That's why we were focused on a strictly decentralized system. We want to achieve scalability, have large anonymous groups like really the swarms. And of course, high density of obstacles because you can imagine the forest. As a first technology we had to design was a relative localization of the robots in the tightly cooperating swarm. We have tried many different methods. We have tried RGB cameras, LiDARs, visual markers, CNN for detection of the robots, and many others. And at the end, kind of we are using in almost all projects that are focused on reliability in the real outdoor environment. This relative localization, which we called UVDAR, it's based on UV LEDs that are installed on our robots. It can be on flying robots as well as on ground robots or even on boats, as I will present you later on. The advantage of this system is that in the spectrum of solar radiation, as you can see on this graph, the UV part of the spectrum is filtered out by the atmosphere, and that's why if we have these UV LEDs and we have a filter which is blocking all the other spectrums before the camera chip, you will get kind of these bright spots, which is the drone, which is very easy to detect, and we can get even some ID if we are blinking with the LEDs. Now we can even communicate kind of indirectly by this visual channel. So it's a very useful technique. I recommend you using this in your multi-robot experiments. We have already maybe 100 users of this technology, not only within our group, so it's already like really mature enough. So this was the first technology we have to design. Another technology which we designed to be able to do this reliable swarming or multi-robot deployment in a real environment was control architecture. We open sourced it. We have now more than 1,000 registered active users. Many robotic groups worldwide are using it. So take a look. It's described in this paper. You may find there many different controllers, linear, non-linear MPC, PID, of course, many different controllers, but also many possible sensors to be integrated. We have designed even some fusion mechanism to fuse multiple sensory modalities like vision, LiDARs, really many of them. Even, I mean, you can get a real drone with such a system in case you would be interested. So you can visit this web page and see the plethora of sensors which can be applied on the drones and which can be directly integrated by that system. And even our spin-off company can ship you the drone in case you would be interested in. And based on like collecting all these basic components, I would say we managed like 3-4 years ago to be really able to fly in the forest. So here you can see a swarm of 4 fully decentralized drones. They are not communicating only by vision. They can see each other. They can be stabilized. They can avoid the obstacle. They can create their own map. They can fly through the forest. So, like, quite nice result, I have to say, but practically not used at all because it's extremely slow. And I will show you why and how to deal with that. Besides that, we have implemented also many flocking mechanisms that are kind of taking inspiration from nature. This is an example of a flocking mechanism that is able to be split into several groups working together. They can fly even without GPS, vision-based stabilization, and you can see the challenging environment of the desert where we have tested. So we have also many experience from the flying above the desert. The system can be applicable in the night as well because we have the active vision to detect the drone. So it's to say true, even work much better during the night time because you don't have any disturbance of the sunlight. And as has been mentioned, we have been also participating in DARPA Subterranean Challenge. We were focused mainly on the drones. We were part of the team of other groups which were working with ground robots. We were deploying the drones in this difficult environment. Thanks to Luca, I can skip these. I don't have to show you all the videos from the tunnels, from this abandoned nuclear power plant where we were flying with a team of drones. Maybe I will show you briefly just one video from the cave system, because no, this is not the one. Sorry. Yes, this one I want to show you because the cave circuit was cancelled due to the COVID, but we managed to fly in the natural caves in the Czech Republic. So these videos are not available at the DARPA SAPTI webpage. And it was quite interesting experience. We were able to deploy a team of flying robots inside quite a huge cave system in Czech Republic. So the drones were managed to fly 10 kilometers at the end, build a map, and you can imagine the difficulties of the deployment of flying robots in such a like really wild conditions. So we had to manage problems of dust, humidity, even water in the cave. And at the end, in the finals, of course, we had to fly in a very challenging environment, which was composed from the tunnel environment, cave systems, as well as of some metro station, which was constructed by the organizers. We managed to get a lot of publications. Yeah, the middle one has been already mentioned here, so maybe this is the best source of information where you can read more about also our drone system. We have also a lot of experiences from the industry deployment of our robots. So this project is being, in fact, motivated by the MBZRC competition in Abu Dhabi, where the task was to firefight by drones or by robots in tall buildings, like these big buildings in Dubai. We got an industrial project with some European company to build firefighting drone. This is a small prototype of the drone. Finally, we designed even a full-scale prototype, and now it's become a product of the company. So this is a single robot kind of deployment so far, but the company is about to deploy these robots. So now you will see the action. The drone is shooting some firefighting capsules into that window to remove the fire. So it's using on board AI to detect the window, the fire inside, and to shoot inside. And the company is currently thinking about multi-robot deployment for forest fires. So it's another interesting multi-robot applications, I hope being soon, but we have to solve the challenges I'm going to tell you about a bit later. There is another industrial project which is already the product is on the market. It's autonomous drone hunter to protect like airports or critical infrastructure, so that the drone is able to capture other drones. We are working on this project together with, again, a European company. They are building mainly the hardware, and we are designing the AI for the drone, I would say. So the robot is equipped with onboard sensors to detect the drone. It uses 3D LiDAR cameras on board, and it's capable of detecting of the flying target. Then once the target is detecting, there is a net released from the drone, and the drone can be catched. Again, so far it's a single robot project only, but you can imagine the multi-robot scenarios, because now the scenarios with multiple targets and multiple drones to be used is kind of critical. So again, we need to solve the list of challenges. I'm going to it now to be able to deploy such a system in multi-robot fashion. So these are the challenges we have identified during our, let's say, 7 years long journey towards the multi-robot deployment. So as I have mentioned, the first one is the agility. Currently, most of the swarm system you can see, if we are talking about drones flying in such an environment like the forest, are pretty slow. We should use like more the capacity of the drones, mobility to be able to solve more problems, and to be able to really get the multi-robot systems or swarming system into the industry. We are currently working on many of these aspects like nonlinear control, fast perception. I will show you a little bit later. Another important aspect is reliability, mainly in case of GNSS denied localization. We have found many problems in degraded environments like the desert, for example, where you don't have visual features. If it's a flat, like a sand desert, you don't have even LiDAR features because there are no obstacles. So this is one kind of challenge that motivated our further research. Another problem is that usually your sensory equipment depends on the environment where you are going to fly, and the capacity of the drones is small, so you can't put all the sensors on it, like in case of cars maybe, or ground robots. So we have to select the sensors properly, but still in many environments you need multimodal perception. You have to combine 3D LiDAR's vision. So this is another work we are currently doing. Another thing which is important is the global localization. So far in the swarms, we are strictly decentralized, and each of the robot is building its own map in its local frame. We don't care about the global deployment, I would say, but in the applications, you have to get the drones into required position, which is usually defined in a global frame. So this is still ongoing research in this direction. And of course, once we are flying fast, we can do long-range missions. For that, you have to create large maps on board of the drone with limited computational power. Another aspect I want to briefly touch is the scalability. So far, I'm talking about swarms, but you could see maximum like 18 robots being deployed, but we are kind of considering really going to hundreds. And then the perception, even the UV there, is failing because you have many objects around, and you are like really the fish in the middle of the fish school. But the fish is able to survive, and they are able to work in the group. So probably there could be a solution. We are working on it right now. And the last point I will mainly tackle, if I have time, is the heterogeneous systems with different dynamics. So each drone, or each different even drones or boats, cars, they have different dynamics. And if they have to form compact groups, we have to modify the algorithms to fit with it. So firstly, let me briefly show you our current results on the fast swarming in plain GNSS denied environments. So in such a plain environment, you can't use usually 3D LiDARs because simply there are no obstacles. You don't have 3D features to use it for localization. It's not like in the city where you have buildings around. We are flying above fields, above the desert. So usually we have to rely on VIO, but even this VIO can have problems. So once flying above the desert, we found many places where none of the sensors is working at all because simply you don't have any features. So we are thinking like, could the other robots help us since we are flying in a swarm? The answer was yes. So this is an example of a deployment of robots where none of the drones is using GPS. Only some of the drones, in this experiment, only one of the flying robots is using VIO for velocity measurement, and the other drones are using this drone as an anchor. So the other drones are stabilized based on the information from the one lucky guy which is currently seeing the visual features. Of course, in this experiment, we simply switched off the VIO completely on the other drones. But in reality, all the drones could be equipped with VIO working properly, but in case of troubles, they can use the advantage of the swarm existence around to be stable. But we wanted to go beyond it. What about if none of the UAVs will use the velocity estimation? So if you have experience with drones, flying robots, you know that if you don't use any of the 3D LiDAR or visual sensors to measure the relative velocity towards the ground, and you will rely on IMU only, you will crash like in a couple of seconds. Like in 2 seconds you will crash. But if we use the swarm kind of presence around, what will happen? You will kind of imagine that you have the UVDAR system, which means that you can measure the relative distances in the swarm. You can fly in the environment and kind of rely on the presence of the other teammates. And all of these guys, they have this huge drift in IMU echolocalization. But this drift is randomly to all directions. So if you sum it together, because you will kind of combine it by observing of the others, the result will be more stable than the single robot. So these three guys were flying randomly somewhere based on the accumulated drift of the sensors, but they were flying. So here you can see an example. The yellow guy is not connected to the blue one, and it's crashing immediately, you know, but the others are still stable. They are flying to random direction, you know, we cannot influence that. We don't have any localization system working. So they are really blind, they can see only each other. And what's interesting, what probably you will believe me, more drones you have, this motion is lower. So if you have, we have tested it with 100 robots and you will get really a stable swarm just hovering. So imagine a situation where you have like GPS jamming or communication jamming, whatever, you can't see any visual features. So still your swarm will survive at least, it will hover, you know, which is very interesting achievement. Even I didn't expect if this, once the PhD student came to me. So this was the research towards the problems with localization. Here I will a little bit speak about scalability. So imagine that you have hundreds of drones around. We did some experiments with 22 drones, and we purposely placed all of them in a view of one localization camera. So we got like pictures or data sets where it's presence of really tens of drones that are overlapping. It's really difficult to recognize them by classical approaches. And we have found quite interesting phenomena in nature that probably the animals in the flocks, in like fish school or insect flocks, they don't rely, like they rely on some neighbors around, just few members probably, and then they use kind of a density of the population around to be able to achieve the compactness of the swarm. And we did the same with the drones here, and we designed a technique which can identify just the neighbors nearby for obstacle avoidance, let's say, and then the density of the swarm, so each of the particle can be stabilized towards the center of gravity of the swarm, kind of. So even if you are in a huge swarm, and you don't know where you are in the swarm, of course, you can just detect the density, and if you are going to the outer of the swarm, you will have like less density here, so the force will get you back to the center, the same way as, for example, insect is doing. So if you are interested more in details, you can see the presentation of one of my students here on Wednesday on aerial systems Another research we are ongoing right now is agile flying. We are not the only group doing agile flying. Probably you could already see Davide Scaramuza's achievements on the drones. Our research is kind of innovative in the fact that we are going really to the wild. So like Davide is extremely good in his like lab conditions. They did a great job. They managed to beat drone racing champion, but we can do this the same in a real outdoor environment. Currently, we are integrating VIO to have really fully autonomous drones flying extremely fast. So once we have a drone, a single drone, which is flying fast and agile, we want to have a system which would allow to detect even the other drones flying extremely agile together. We are now designing a relative localization based on event-based camera. Probably you have heard also from Davide about event-based camera. And here are some results of 2 drones flying extremely fast. This is like less than 1% of the real time. So it's like slowed down extremely. So you can see even the rotation of the props. So by the way, this is one of the important elements we are going to use for detection and relative localization, the frequency of the props. There are some promising results. We have submitted a paper, so hopefully we will present it on IROS. Regarding the heterogeneity of the swarms or multi-robot systems, we have now multiple projects on like marine operations. We are working on stabilization of teams of flying robots and floating robots, boats. Even we have tested submarines. So you can imagine the difficulties there. For example, I don't know why the video is not running. Codec is not available on this computer. So you would see a great video of a boat which is going in waves, and there is a drone landing on that boat. No, really, I'm not kidding. You can see the paper. and even currently we are working on a mechanism where the drone and the boat are coordinated in the way that they can cooperatively manipulate an object. So here we have to keep with the dynamic. There is another presentation on Wednesday. I forgot to edit to the slides regarding this project. It's on heterogeneous planning, because also for the motion planning you have to, of course, take into consideration the different dynamic models. So find my name on Wednesday, and it's a RAL paper presentation. Okay, so I'm going to conclude my talk. I have 2 offers for you. The first one is the Open Remote Laboratory. We are running already the 2nd year. We have 1 year ahead of us. It's funded by European Union. We are getting money to help you with experiments. So in case you would like to do some experiments in real world conditions, but you are flying indoor only in a drone arena, or you have just simulator and no real drones, just drop me email. You can register there, and we can really do like the experiments in the wild. We done this, the last round was like 2 weeks ago. We did 8 experiments for people from different countries. There was even one student, he did like 20 drones experiments like in the forest. So it was really amazing how easy was the transfer from simulations only to real environment. So in case of your student would be interested, just let me know. Another event I'm going to tell you about is our summer school. We are organizing already this 6th year summer school on multi-robot systems. So in case your student or you would like to participate, we have still few slots available. The capacity is almost full because we have a limit. We are limited by 240 participants this year. The lecture hall is such a big. We have excellent list of lecturers. I have here some leaflets, so in case you would like to register or limit your students, feel free to grab a leaflet. And now, probably time for a question.
Thanks, Martin. Okay, so any questions? Luca.
Fantastic talk. So congrats, great work. I have a question maybe about the work in which you're putting multiple IMUs on multiple robots to reduce the drift that you're fusing information. Have you guys tried putting multiple IMUs on the same robot as well? Like, would you get the same benefits from that? I know that there are companies doing that, but I don't know if in that case there is more correlation between the biases.
We have never tried it, but definitely you will try it. Thank you for the good hint. But it's boring, because company can do it, this is more research. But yes, good idea.
I have a question. What sort of accuracy do you need for deploying the drones in the woods scenario? Accuracy of in the localization, or what?
Yes, so it's pretty accurate. So it depends on the sensor. So we have managed to be flying in the forest just with a simple 2D LiDAR. And the accuracy was then like after, let's say, 15 minutes flight, meters. But now we have tested the new 3D LiDAR, and the accuracy is around centimeters, maybe after 15 minutes of flight. So we are now able to fly maybe a few kilometers even in the forest with really extremely small drift in the localization. Kind of the environment is pretty good for the localization. You have the trees around, and so you can do pretty well the slab. But we cannot close the loop because the trees are almost the same everywhere. So this is tricky, but
yeah, I was thinking in vision, and I thought that could be very tricky for vision, but yeah, with LiDAR.
Yeah, that's why we usually use 3D LiDAR. But probably no, we have tested VIO as well, and it works also pretty well.
Okay.
But again, as an odometry, right? So you can't
close loops.
You can't close the loop.
Yeah. Thank you.
Thank you for your presentation. I'm wondering if there is some strategy to maximize the probability of mutual detection, something like that, to ensure the robustness of the multi-robot localization.
So you're talking like asking about the reliability of the system?
No, I'm curious about how you maximize the probability of mutual detection, because in your system you have a visual detection module to relook. Yeah. I think I see the camera seems to be FOV limited, or is
yeah. I mean, our solution is simply to use more cameras. So we have usually the fisheye, which covers like more than 100
Okay. Yeah.
So we can put 2 cameras to get almost completely the surrounding. Of course, there are some blind spots above and below the drone. So with 3 cameras, we are able to complete the ball, to cover the ball completely.
Okay, thank you.
Okay, and last question.
Hi, thank you for your talk. The quick questions about your agile drones, in particular on the state estimation part. You mentioned you're going to use VIO for state estimation. So the questions are 2, 1, what are the challenges? And 2, how do do you plan to deal with motion blur if you're going to fly really fast, which I guess is one of the major challenges in BIO for agile flight?
Exactly, of course. So we have everything. It's working pretty well if you are flying 5 or more seconds. Clearly, it's the same as if you are close and flying slow. But we want to fly through the forest, so we need already some tests there, and it's extremely difficult conditions because you don't have enough light there. The light is changing, so even this is the problem. So even before the image blur, you have a problem with like changing the light conditions quite extremely, for flying out to the forest. And regarding the motion blur, I mean, some techniques work, some don't. Even we are testing right now the event-based camera, so we need some data sets, so in case somebody will be interested, we can share the data set from the forest, where the drone was flying pretty fast through the controlled environment, so we found some, fast in the forest. It was not so dangerous for the drone, but we got the data of the trees flying extremely, flying fast around us. So from event-based camera, it looks pretty good, but it's ongoing research.
It might use it that they apply.
Probably. It's really not solved yet.
All right. Thank you.
Thank you for the question.
Well, thank you very much for your great talk. With this, we conclude the second session.